Welcome back to the Deep Dive. We're continuing our series for number theory students, and today we're tackling a sequence that's, well, proving surprisingly challenging. It's A000293, known as solid partitions. Our mission today, really unpack what these are, look at their unique features, and figure out why this sequence is so significant, maybe even a bit notorious in math.
Right. And what's really fascinating here, I think, is the jump in complexity. An ordinary partition, that's just arranging numbers in a row, maybe visualized in 2D sometimes. But with solid partitions, we're actually talking about arranging items like unit blocks in, a three-dimensional pile. The key rule is that the numbers, or blocks if you prefer, must be non-decreasing as you move away from the origin along the X, Y, and Z axis.
Okay.
It's that jump, that move from 2D thinking to 3D that really changes the game fundamentally.
Right, okay, 3D. So let's look at the sequence itself. The first few terms go 1, 1, 4, 10, 26, and so on. The first term, A1, is 1. That seems simple enough. But when we talk about these three-dimensional piles, what are these numbers actually like counting?
Yeah, good question. How do we visualize these things? Let's take 8, 2 equals 4. So there are 4 ways to arrange 2 units in 3D following that non-decreasing rule. One way is just stacking them, like a single block representing 2. Straightforward. The other 3 ways are more like an L shape. You have 1 unit at the origin, 0, 0, 0, and the second unit can be placed right next to it along the x-axis or the y-axis or the z-axis.
Okay, so like 4, 0, 1, 0, or 0, 1, 1 relative to the first block.
Exactly. So that gives you the 4 ways for N2.
Okay, that makes sense. What about A3 equal 10? I imagine it gets complicated quickly.
It really does. For A3, the complexity jumps up fast. You're arranging 3 units now. You can have 3 itself, or 21 in various orientations, or 11 arranged in different 3D shapes. These aren't just random stacks, though. There's structure. They're sometimes described as chains of integer partitions.
Chains of chains, what does that mean?
Well, you can sort of think of it like layers or slices of the 3D structure. Each slice might look like a traditional 2D partition, and these layers then link together according to the rules. It's this kind of nested complexity, this hierarchical structure, that makes them, well, uniquely challenging to count.
Okay. And I gather this leads to something quite unexpected. Because here's where it gets really interesting, right? You mentioned the complexity. Despite this definition seeming somewhat straightforward, maybe deceptively so, finding a generating function for solid partitions, well, it's an unsolved problem.
That's absolutely right.
Which is pretty significant in combinatorics.
Yeah.
And apparently, it was even mistaken for a different sequence, A000294, initially.
Yes, that's a historical note. Finding that generating function, that single algebraic expression that would encode the whole sequence, it's a major open question. And this unsolved problem, it really points to the depth here. It means A000293 isn't just some mathematical curiosity tucked away in a corner. It actually has quite diverse applications and connections that people are actively exploring.
Like what sort of areas?
Well, you see it popping up in graph theory, maybe related to certain kinds of network structures. And in physics, too. Sometimes it connects to models of, say, crystal growth, or perhaps certain problems in statistical mechanics.
Really? Physics?
Yeah. And current research, looking at papers by researchers like Suresh Govindarajan or going back to the work of McMahon, they're actively studying the asymptotics of these things, so how these solid partitions behave when it gets really, really large.
Higher dimensional partitions. So this is still very much an active area.
Absolutely. It's pushing the boundaries of what we understand about enumerating complex combinatorial objects. It's a genuine frontier. The fact that something defined so, you might say, simply, can hide such deep mathematical puzzles. That's what makes this field so captivating, I think.
So wrapping this up then, what's the main takeaway for our listeners? It seems like A000293, this solid partition sequence, it really stands as a testament to the ongoing frontiers in number theory and combinatorics. Even definitions that appear simple on the surface can lead to some profound and, importantly, still unsolved mathematical problems.
Exactly. And maybe it leaves us with a provocative thought, this pursuit of an unsolved problem, like finding this generating function. How does that actually push the boundaries of our mathematical understanding? And maybe more fundamentally, what new tools, what new ideas or techniques might mathematicians need to invent to finally crack this one?
A really active frontier. That's all the time we have for this deep dive into OEIS sequence A000293. Hopefully you found some surprising insights into the world of solid partitions. Thanks for joining us.